Good morning. You may wonder what I'm doing standing here in the dark. Well, I'm going to show you an apparatus called the Geissler Tube apparatus. And the Geissler Tube apparatus utilizes these glass tubes that have metal electrodes in each end. There's one here and one here. You probably can't see it from where you're at. And they're filled with one gas. And I'm going to use this apparatus to demonstrate what happens when you add energy to an atom. This first tube is filled with hydrogen, and that's all that's in it other than the two electrodes. And this tool right here is going to add energy. The reason I'm in the dark is to provide a little more contrast so you can see. Students who are in class will be able to look at this through a diffraction grating. A diffraction grating is basically like a prism in that it splits the light into its colors of light. Every time you see light, it's a mix of colors. White light is all the colors. Roy G. Both, there is no actual indigo anymore. But red, orange, yellow, blue, green, violet. And so we're going to look at hydrogen. Those of you who are at home, I'm going to ask that you write down the color you see, but then you look up online the emission spectra for hydrogen and then write down the 4 brightest colors. And by brightest, usually in a spectra, that'll mean the whitest line. You'll see what I mean in a minute. But here is hydrogen. I'm going to turn off the light in just a second. So when we energize hydrogen, you can see, hopefully in this video, that it gives off kind of a lavendery light. Why does it do that? Well, when you add energy to an atom, it absorbs it in the electrons. The electrons are in various energy levels, and what we assume happens is that as energy comes into the atom, the electrons absorb that energy and jump up to higher energy levels. Well, the thing is they can't stay up there. That's not where they belong. So eventually, they go back down to their original energy level, and in doing so, they have to release that energy that they absorbed. Well, they release it as photons of light. Because every element has a different number of electrons and a different electron configuration, every element will also give off different combinations of photons of light and thus a different color. So what you're seeing here is the blend of those colors. If you look at an emission spectrum, what you'll see are the individual wavelengths of those colors that combine to make this. So that was hydrogen. Hydrogen is the smallest atom. And so it only has 1 electron and 1 proton. We're going to look next at the second smallest atom, which is helium. So helium has 2 electrons. Sorry about the darkness, but that's the only way we can really see this. So it's a little hard to see from the video at home, but this is kind of giving off more of a peach color. Let's see if I can get any closer. Oh no, does not really show the color very well. So, but helium now has 2 electrons that can move around. So as we are adding energy to the helium is jumping up, the helium electrons, are jumping up to higher levels. In order to drop back down, they have to give off distinct photons of light. Remember, a photon of light is just kind of like a little packet of light. Light is unusual in that it exhibits both the characteristics of particles, and that's what we mean by photon, it's like a little packet of light, but also of waves. You remember probably studying waves in middle school, and and the way that things can move in a wave with a peak and a crest and all that good stuff. So once again, if we broke this down into its individual wavelengths of light, that would be the emission spectra of helium that combine to make, when you're in person, a kind of peach-colored light. So the noble gases are super handy for studying this. So another one that we can look at is neon. And of course, neon lights are famous for, you know, in Las Vegas. It was one of the earlier lighting, types of lighting that we used. This one is a very vivid dark orange. Once again, that's a little hard to see in the video. In person, it's a lot more vivid. Neon has 10 electrons. Those electrons, when they're energized, jump up to higher energy levels. In order to go back down, they have to emit photons of light. And those photons combine to give you an overall color of orangey red. Again, it's not terribly representative on the video that I'm looking at now. It doesn't look quite the same. But if we looked at those through a prism or through a diffraction grating, we would see that it's actually all these individual bars of light that combine to give us that color. Another noble gas we can look at is argon. This one you can see a little bit better. It's kind of a pale blue. You can see some of them glow a little brighter than others. I can actually hear the light jumping. You can kind of see it at the top of that bulb, that Geissler tube. So, I know I'm saying this over and over, but why does argon give off this specific color? Well, as we add energy to argon in this tube, we got the two electrodes adding electricity. The electrons absorb that energy. They jump from the energy level they're on up to higher energy levels in the atom. And in order to go back down, they give off photons of light. Different numbers of electrons and different elements mean they each have different colors of light. So you notice that these are all gases. There is actually one metal that we can get into a Geissler tube apparatus, and that's mercury. You may remember mercury is a liquid at room temperature. You'll notice that its color is actually somewhat similar to argon, but if you looked at its emission spectrum, all the bars of light that make it up, you see that even though the colors add up to be somewhat similar, the emission spectrum is quite different. So what I'm going to have you do, those of you who are at home, because you cannot look through because you can't look through the diffraction grating to see the emission spectrum, I'm going to have you look these up and then note which bars of color are the thickest. So I'm going to pause this for just a second so I can give you an example of what I want you to look at. Okay, so I have shown you the lights. I know at home that wasn't terribly exciting because you could not see them horribly vividly. But once you've written down those initial colors, and I kind of verbalized them to you, what you're going to do is for each of those elements, you are going to look up their atomic spectra. And I have given you a handy dandy link to do that. So go to your class in Canvas, and you will find a link in modules where I put everything that will help you identify the spectra that I want you to find. Now, when you get here to this periodic table, make sure you're seeing this, you are. You'll notice that it has every element, and you're simply going to click on the ones that we did today. So what do I want from you? Well, some of them are quite simple. You're going to click on hydrogen, for example, and you'll see that hydrogen only has 4 bars of light. That's not horribly surprising. It only has 1 electron. And so what you're going to do is write down those bars, those emission spectra, that's what we call them. They are the spectral lines of the photons of light that are emitted when we energize hydrogen. And you're just going to write them down in order. So what is that, like a purple or a violet, blue, a teal green, and a red. And then you're going to write down which one is the most prominent. Well, how do you know which one's the most prominent? By the thickness of the bar. For example, if you look at this red, it seems thicker than this blue. And so you're just going to fill in your table using these. Now, when we go back to pick some other ones, like if I picked carbon, carbon isn't one that we're doing. But what you can see is sometimes they can have lots of lines. So I just want you to pick the 4 to you that look the most prominent. For the other ones, argon, helium, neon, mercury, and fill in the activity that I gave you. It is kind of fun to look through some of these different ones. Aluminum, wow, it only has 3 bars. I mean, I always find that fascinating how some of them have a lot and some of them have a little. Look at iridium. Wow, that is a lot of bars. One reason that we do the Geissler tube with a specific set is we try to pick some that don't have as many bars of light. We can get metals to go into gaseous form with the right pressure combination, but there's no really need to do that, because this is really just to show you what happens when we add energy to an atom. So make sure you have the colors from the Geissler tube apparatus. Rewind to see those if you need to. For each element that I did up here, I think there's 5, you will need to fill in your in the worksheets. In your DIN, the part on their bars of color, their emission spectra. And you get to pick the 4 that seem the most prominent to you, and then you'll label them most and least of the ones you selected. And then that will be the end of this activity, with the exception of you kind of reiterating what I've explained is happening. When we add energy to the atoms, they absorb that energy in their electrons, and the electrons use that energy to jump up to higher energy levels. In order to drop back down to their original location, they give off photons of light. Every element has a different number of electrons, therefore they all have different combinations of wavelengths they emit, which means they give off a different color. Sometimes the colors are really similar, but in this case we're okay. The ones that we're having are pretty different. So I'm going to let you get to that, and good luck.